Okie dokie. 8. So the only two things he wants us to know is ionization energy and electron affinity. So I'm gonna write that down. Does anyone know what it is?
I know nothing on this chapter, if I'm being totally honest. I think I might have been absent this class.
Okay, so I'm gonna write down the definition. And then I'll simplify it after. So this is the definition of ionization energy. The minimum energy required to remove an electron from a gaseous atom in its ground state. In other words, it's the amount of energy in kilojoules it needs to strip 1 mole of electrons from 1 mole of gaseous atom. In simpler terms, how I like to call it is just the removal of an electron of an atom or element that forms a cation. So pretty much when we remove an atom from and we remove an electron from an atom or element, it becomes a positive charge. It becomes a cation, so a positive. So ionization energy just means it's the energy that you need to remove that electron. So give you a visual on it. Do that. I'm gonna use lithium as an example because it only has 3 electrons. So I want to remove this. I want to remove that. So I need to do ionization energy to get rid of it, to get it go away, to become just 2 electrons. So that's pretty much what ionization energy is. How do we do it? It doesn't tell you how. He just wants to know the term and what it is and what it does. I mean, I just wanted to just on just what it is. The process. And how do I put this? So the term I have for here for this would be this. These are the key symbols I want you guys to remember because I'm about to write the process. These are the symbols I want you to remember right now. Negative means the removal of electron. X just means an atom of any element. And IE is the ionization energy. So what's the, how do I say this? So depending on how many electrons the element or atom has, the more energy you need to remove it. So the less electrons it has, the less energy it requires. So for example, lithium right here, this thing, we need low energy because right now it's not enough, it doesn't produce enough, you don't have a lot of electrons to remove it. So, and as you know about the electrons, they all repel each other. So this here this is a proton, right? So it's a positive charge. This is an electron, so it gives a negative charge. Electrons repel each other. And protons, the plus, and electrons attract. So electrons repel, protons and electrons attract. And what I mean by that is because going back to this here, there's an attraction. They're all attracted to the proton in this element. So all these electrons are attracted to this proton. So according to lithium, it has a proton of three protons in there. So you need 3 electrons to make it a balance. So what ionization does, the ionization energy, what it does is that we're going to remove one of these electrons. So when we add the ionization energy, i.e., we're taking away 1 electron, goes away, so it just becomes 2 electrons. And the outer shell goes away. That's how it looks when we get rid of the electron. But the proton inside does not change. It's still, the charge is still 3. So in this case, this has a +3 with a -2, which equals just a +1 charge. That's what ionization means. It makes it positive because of the protons in there. Questions?
Does that mean the ionization energy for Li is like it's 2 minus 2?
No, it's not math. It has nothing to do with math. It's just a
Okay.
process that's happening.
Okay.
-2 just means you have 2 negative electrons on the element. This here becomes Li +1, or just plus.
Oh, like if the professor asks the ionization energy of Li, it's just write Li plus.
Okay, so
what to say?
okay, so let me give you all right, so here's another one. Here's another thing I want you to know. The level, ionization level, it increases depending on the number of electrons or element has.
Okay.
So this here is ionization 1. This is 1. Because we remove 1 electron.
Okay.
So let me go with another element. I use lithium because lithium only had 1. So let me use another one. Let me see, which one did I have here that I can use? All right, let's go with oxygen. You know how many electrons the oxygen has
8.
in total, right?
Yes.
All right, so I'm gonna write it here. Oxygen, we have a total of 8 electrons. So that means you have -8. And how many protons?
8.
8. So we have 8 electrons and 8 protons. So that means this element is what?
Neutral.
Neutral. 0. Neutral. So we're gonna do ionization, the first one, IE1. We're gonna remove 1 electron. So now we have 7 electrons with a proton of 8 plus 1. So now this O becomes O plus
Okay.
because we remove 1 electron. It's plus 1.
So by adding the ionization energy, you're just removing an electron.
Pretty much, yep, that's it. That's the simple definition, yes. This is level 1. If you want to do 2, then we have to continue on with this element and just continue on. We have to continue on with this ionization energy. We start from here. We can't start from neutral. We continue on from here.
You continue from +0?
Yes. O plus. It's not a 0, it's oxygen.
Oh, okay, gotcha.
The element is oxygen. So we're going to continue on from O plus, which is this. We have -7 plus 8. We got 1. So now we're going to remove another one. How many electrons do we have now?
6.
This process is called the next level, i.e. 2. So we have 6 with a +8.
So it'll be a +2 charge.
+2 charge, yeah. And the element would be 2. Oops. Like that.
Oxygen with a +2 charge.
Yep.
And how far would we like have to go?
Well, it depends on the experiment.
Okay,
That depends on the experiments and how much you want to remove.
gotcha.
This is just the process, that how it works. It's showing you the tool.
Mm-hmm. Okay.
So that's ionization energy. So if you want to do IE3,
-5 +8 +3 charge.
yes, we remove another electron. All we have left is -5 with a +8. The protons never move, it stay the same. And it's because of +3.
So how will I know how many electron I have to remove them?
Depending on the experiments you're going to do.
Okay.
If you're going to make an experiment right now, you want to remove electrons, up to you how many you want to remove. You're using ionization energy to remove it.
Okay.
So say you find an element with this, say you find an element that's this right here. You want to remove an electron, so you use ionization energy, you become here. It will turn into this.
Okay.
So it depends on the experiment or what you're doing. It's just a process of how it works.
All right.
Questions?
I just have one question. You see how you on the beginning of it kind of missed that portion. When you and Imani was talking, you said -A plus A proton and electron, they have to coincide together of the element of oxygen.
This is where
And it's
the
a neutral?
isotopes comes along. This is
Okay.
isotopes. This is what becomes the isotopes. This is a neutral when this is normal. When it has the same amount of electrons and protons, that's normal. That's considered neutral.
Yeah, but
Once
sorry to cut you off. So how will you know there is neutral? It, how will you know
that
when it
is
has
neutral,
yeah.
all elements are neutral.
Okay, gotcha. All right.
All elements are neutral depending on what you're using, depending on how you play with them.
Okay, gotcha. Understood. Thanks.
Yes, all elements are neutral. Hydrogen. How many protons does it have?
One.
One proton. And how many electrons?
One.
There you go. Neutral.
Hi, guys.
A
Hey, so Johnny.
Yay.
Okay. Cool. I just missed that first portion. That's how I was just
Oh, that part
uh,
confused you?
no, I just got thrown off. Like then I see that first portion and then now I understand
Okay.
it. Thank you.
All right. So that's the ionization energy. All elements are neutral. You use ionization energy on the elements, it becomes positive. You're
Huh?
removing you're removing the negative. So the more negative you remove, the more positive it is because you're having less electrons on it, and the protons never move. Never yeah, they can't be removed, they stay the same. So you guys want to do some practice with this? Practice problems?
Yeah.
Yes.
All right. I'm still sticking with the top 10 elements. I'm gonna do any. How many protons?
10.
And
And how many electrons?
10.
10.
Where do we get that? On the periodic table?
yes.
So this is we're just gonna play with this. This is not how it actually works, but we're just gonna play with it. Um, give me these. Oops, give me these. IE1, IE2, IE3, and IE4. The name of the element in IE1, 2, 3, and 4. You gonna need more minutes or can we go? Let's start.
We could start.
We can
All right.
start.
What would be the IE for what would be the NE in IE1? How would we call it?
Any plus?
NE plus. And for IE2?
And E plus
And-
2.
NE plus 2. Yep.
Okay.
And IE3?
Any plus 3?
NE plus 3. That's how simple it is.
Yeah, this is
Got
really
it.
simple. Is this all it is?
Yeah, that's I'm telling you, it's very simple. How many electrons would be in NE1 and NE plus?
1.
How many
No,
electrons?
no.
Eight.
-9 electrons, right? And this
Mhm.
one?
8.
8. This one will be 7 and this one will be 6. So the more plus we have, the less electrons we have. This is also known as a cation. So when the element is plus, it's a cation. It's a plus charge.
You said when the element is plus is cation.
When the element is plus, it's a cation.
But where on the chart do you see that it's plus 10 and negative 10? Sorry, I came in late to this, so.
This is ionization energy. This is the removal of electrons.
So, yeah. So,
She
Johnny,
has the same question that I did, that she stated what is plus 10 minus 10. David stated saying that all elements are neutral. Protons are 10, electrons are minus 10. That's why it's like that.
Okay, so they're all plus 10 and minus 10?
All
All el-
electrons, all the elements are neutral. So I'm gonna give you, let's go with this one. Let's do carbon. Carbon. How many protons does carbon have, Johnny?
Uh, 6?
Right. So we have 6 protons. That means we have,
Negative 6 electrons?
yep. So that's what makes it a balance.
Okay.
That's what
So
makes it
then,
neutral. So when we use,
IE1 for carbon would be plus, and then would be plus 2.
it would just be C plus.
Right, and then
IE2.
IE2 would be C plus 2.
Because in this way, in this one, we have 5 electrons and we have 5 protons. Means 6 protons. That would equal a +1 charge. This one here, we have 4 electrons, still same 6 protons. Charge of +2. That 2 is this 2. This 1 is this 1. So the amount of the higher the more electrons you have, the more energy it requires to use.
And because it's plus 2, it will consider a cation, right?
Because it's a plus, because it has a plus on it, it's considered a cation, yes. Cations are plus. How you can remember cation? Let me write it down. Cation. This is how I remember it. You see the T?
Yep.
It looks like a plus. So you see the word cation, it just means plus. The element is a cation, that means the element is a plus. It's a plus charge. And that's ionization energy. Questions? No questions?
Can we do one more example just to make sure that I got this?
Okay, let's do sodium.
Okay.
What's the element for sodium?
S.
No.
Na.
Na.
Oh, sodium, Na, sorry.
Na. How many protons does it have?
11?
11.
How many electrons?
11.
So this equals, so it's 11 protons, 11 electrons, so this is a neutral charge. So we're gonna do IE1. Na becomes what?
Na plus.
Na plus. Because now Na plus, we have still the same 11 protons, but now we would just take away 1 electron. Now we have 10. So you get the +1 charge. Want to see the picture, what I mean, I'll show you.
David got fancy with his diagrams here.
All right, so this is basically what we did. This is ionization energy. You see, we have 11 electrons, right? So Johnny,
Yes.
you see we have 11 electrons. This is ionization energy. We just removed it. Now we have 10 electrons right there. There's, in here, we have 11 protons. Maybe they're in color. This never changes. We're just playing with the outside. The inside stays the same.
Okay.
So the more electrons you move, the more positive it is because of the protons in there.
Protons are positive. Okay.
So on the periodic table, well, I don't want to touch that part yet. So I'm gonna give that as a review summary. So that's pretty much what ionization energy is. So the process, how it's written in books and how he gave it to us is this. Hold on, let's check this out. That's the process. Ionization energy 1, you need the energy, plus the element in a gaseous form becomes a positive with the removal of electron. Second level, we continue on. Energy, we need more energy now, plus the positive one. Now you get 2, plus 2 charge with the removal of with electron going away. Does this make sense?
So your energy here is gonna always be the number you're starting with?
No, the energy is the amount of energy you need to remove it. It's based on kjoules. He's not gonna be like how much energy we need to remove this much. It's just the concept. We need energy to remove the electrons and ionization energy.
So when you're saying he's not gonna ask he's not gonna ask for it to be calculated?
There's no math for this one. There is math, but he's not gonna test us on the math.
Okay. But we need to know this.
And the definition is right there.
So energy plus, that's the element.
X is the an atom of any element. Yes.
Okay. And
Oops. Okay. I'll bring that back. Hold on. That. The E negative just means removal of electron. The X just means any an atom of any element, and IE is the ionization energy, the level.
And what do you do with that? I'm confused. Like
Do
I'm
with-
staring at it and I'm just confused. Like I'm just lost.
You mean the chart?
Yeah, the chart.
Just pretty much explaining to you that it's the same, the pattern repeats, but you're gonna need more energy as you the more electrons you remove.
Gotcha. So like that's not an extra thing to learn. That's just explaining it. Okay.
Because you see, we just removed has how it works is this way. Let me explain. Remember, each electron is all electron repels the electron, right? So these guys are repelling each other. All of these guys are repelling each other. But they're not going away because of this guy right here. So they're all pulling them towards the center. So when I remove this one, when this one was removed, this is the farthest away, right? But it's still being repelled to here. It's the farthest, but it's being repelled. But that means you're gonna require less energy to remove it because it's the farthest away. But the closer you are to the center, the stronger it is to pull it apart.
Okay.
So see it as this way. How I like to explain it is more like this. Everyone's holding hands. You have 5 people holding hands. One is touching the wall. Who's the easy ones to remove from the wall?
The people farthest away from the wall.
The last one that's farthest away from the wall, right? But it's going to require more energy to remove the one that's in front of the wall because you need to get rid of the other electrons. So that's what the ionization means. Ionization energy means. So the more electrons you remove, the greater the energy you need. The more energy you need to take it away.
Okay.
Any questions?
No, I think I understand it.
All right. So if you guys understand ionization energy, then electron affinity should be easy because it's just the opposite. Electron affinity. Anyone know the definition of this?
Yeah,
Because we need to know the definition.
yeah. Electron affinity, the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous state to form an now.
The negative energy change that occurs when an electron is accepted by an atom in the gaseous state to form an anion. You guys know what an anion is, right?
Negative charge.
That's when it has a negative charge, right?
Yep. And how I remember it is because of this, the N.
The
N for negative. N for negative. This negative?
Positive.
That's positive, right?
Yeah.
Why?
Because it's a cation.
Oh yeah, it's a cation, but what's the trick we use to figure out it's positive?
The T.
The T.
The T. The T makes the positives. Looks exactly like the positive sign. So that's how you can tell the difference between an anion and a cation. So going back to this, electron affinity is the opposite. So how, but the thing is that we're not using energy to give an electron. We're not using energy. We're just adding to it. You could just add an electron. But the electron only gets added depending on the element. That's how the electrons get added. So these are the symbols I want you to know for this one, because I also have a chart for this. And this is the chart. Can you guys see it? So what we're doing is we're taking the element, add the electron, and it becomes negative. And it gives off a negative energy. So when the element is already negative, we're adding another electron, it becomes double negative. And so on. So it's the same thing, now it's the opposite. So for the visual example, let's use oxygen again. Right? 2, 3, 4, 5, 6. Oops, too much. Right? Oh, no, it has 8 electrons total, right? 2, 2, 3, 4, 5, 6, 8. Yes. So this is the element of oxygen. How many protons?
8,
8. How many electrons?
8.
8.
8. So it's neutral. So how we make it negative? We're just gonna add another guy.
Add another electron.
But we can't wait. So there's like, wait, 1, 2, 3, 4, 5, 6, 7. Yeah, so we're adding another electron. So now we're gonna have a +8, and now we have a -9.
-9, yeah.
This becomes a -1. So O becomes O negative. And it continues on like that. The more electrons you have, the more negative it becomes. Electron means negative. So the more negative you add to it, the more negative it becomes. The less negative you remove, the more positive it becomes. So electron affinity, it's just basically this concept that's happening. This became a negative. It's like electron affinity. Questions?
So you said, yeah, he's not gonna ask for this part, but for the chart, we're not gonna use this.
For the what?
Oh, you said he's not gonna ask for this part, like he's gonna ask for the chart, right? Like the formula.
The formula?
Yeah,
It's not a formula.
the chart you just show us.
I don't think he's gonna ask for the chart. He just wants to understand how it works.
So if he asks what we should answer then, like I am confused.
What do you mean?
If he asks like what we should answer, if like answer this part or the chart.
He's concerned what kind of questions he will be asking, if it will be based on the chart or based on what we're doing at this point in time.
Exactly, thank you.
But David's saying that he just wants us to understand how does this work.
Because I don't know how he's gonna ask those questions. Because on the review, there's nothing about that. He just says know it.
Oh, okay.
Yeah, because in the review, it just doesn't give us any like problems with electron affinity or ionization energy. He just wants you to know what it is. Because I'm looking at the review sheet right now. All I see is the dot structures, the off-bar order, electronical configuration, the quantum numbers. He said the typical questions on it, which is on the last 3 sheets. He said typical questions that he will ask you. Yeah, that's what I see. And the Bohr atomic theory, the electromagnetic radiation. Yeah, he doesn't cover he doesn't give you any questions on ionization energy or electron affinity. But
Okay.
if you understand the process, Lewis dot structures make sense on how they're positive and negative. Because what makes it a positive is that we removed an electron. What makes it a negative is that we added an electron. Remember the math yesterday? Hope? Hope?
Yeah.
You remember the math yesterday that we was doing with the plus and negative?
Yes.
Yeah, so that's pretty much it. If you know the ionization energy and all that other stuff, that's pretty much what it took, what it happened to create that element. So that's all chapter 8.
Oh.
Just those 2 things. So to give you a really good one that's happening together at the same time, ionization energy and electron affinity that's happening, I'm gonna give you the most common one that everyone knows. Give me a second, let me pull it up. The chemical formula for salt. So I'm gonna do Na. And I'm gonna do Cl. How many electrons does Na have?
11.
11. 2 in the middle, 8. No, 2 in the center, 8 in the middle. 8 and 1 on the outside. How many electrons does chlorine have?
17.
Check again.
Mm,
17, you said? Wait, sorry, yeah. So I wrote this wrong. All right. So that's it. This is chlorine and that's sodium. This one has 17 and this one has 11. But when it comes to this, ionization energy and electron affinity, it's mostly like, in other words, one is absorbing and the other one is releasing. So this one here is releasing this electron to go here, and this one here is absorbing it. So when this ionization energy, this is going over here, Na becomes what?
Positive.
Na plus, right?
Mhm.
The electron is now here.
Yes.
The electron is now here. We received an electron here now. Cl becomes what?
A negative charge.
Negative charge. And you know about Na plus negative Cl, that becomes a what? What kind of bond is that?
Covalent.
Nope. Ionic bond.
Okay, so
This is just, everything just happened all at once together.
yeah,
We just did ionization energy. This just donated the electron to this one. That's ionization energy, the energy required, because the Cl is pulling that energy into this, and then and then electron affinity, it just happened at the same time, which it became a negative. Yes, Anderson.
How will we know when it becomes ionic? What makes it ionic? That's much better.
What makes it an ionic? Okay.
Yes.
One has to receive and one has to give. That's the thing. This can receive and this cannot how do I call it? Remember how many electrons this thing has? How many protons this Na has?
Yeah. 11.
How many protons? 11, right?
Mm-hmm.
And this one has 17 protons. So which is stronger?
The 17.
The 17.
It's trying to compensate.
Mm-hmm. So
Okay.
it removes the electron to on this side. So this became a plus and this became a negative. So it's whatever element you're connecting it to, it's create the ionic bond.
so
Okay.
if the element that has more protons is going to be the one that's going to give off the energy?
Pull, receive.
Oh, because it's stronger.
Yes.
Okay.
This cannot receive nothing at all. It has 11 power. So it's enough with it, just the maximum it can hold is 11. This has a strong power of 17. So it can hold 17 plus one more. And another thing that helps it as well, how many electrons are in the valence of this shell?
Of which shell?
Of the Cl?
1, 2, 3,
7.
7.
Nope, count again.
8.
8, because we added the extra electron.
Oh,
So now this is a valence of 8. This is happy. This one still is also happy because their valence is now this one. This shell goes away.
So it burns down to 10 and makes it a full, and the other one is a full.
Mm-hmm. Because they're helping each other. This one became a positive charge, this became a negative charge, it became an ionic bond. Ionic just means two charges equal together, two charges connect to each other. It has to be a plus or a negative. Another one that we commonly known is water. H2O. You guys know the structure for this, right?
what do you mean by structure?
The 2 H's on the side and O in the middle, connected.
Right? So I'm gonna write it over here so you can guys see that image better. And now I'm gonna draw the atoms. That's what I'm doing that one. Let's do this. Eight. All right, so this is the element of water. How they're bonding is this. Ionization energy. This element going here. This electron is going there, sorry, and this electron is going here. And this also is doing ionization energy. This electron goes here, and this electron goes here. At the same time, they're doing electron affinity because it's absorbing the electron. Well, let me put it here. So if you remember, how many electrons do we have? How many electrons and protons does hydrogen have?
8,
Hydrogen,
1.
one of each, right? So so hydrogen needs 1 electron to be happy with to compensate with the 1 proton it has. This one has how many? How much does oxygen have?
6.
6. So this needs a charge of 6 electrons to be happy with the charge of 6 protons. So that's basically what's happening here. They're all sharing electrons with each other and they're all keeping happy. This element here can have the shell can have a maximum of 8. So when we give off the energy, H becomes a negative. No, a positive, sorry. H becomes a positive. Because when we remove the electron, it becomes a positive. And once it comes back, it becomes neutral. So that's how it goes. Neutral, positive, neutral, positive, neutral. That's how it's happening, the circularization, like that. This one becomes the O negative. This is also an ionic bond kind of way, but it's very weak. And what questions, or you guys understand it?
Understood.
Anyone else?
It's basically like getting on the highway, going back and on the highway, going on, coming off.
Mm-hmm.
Like
If you can
like a
understand it
figure
like
eight.
that as well, yeah. The electron, you're going onto the highway, and then the electron comes out of the highway, back home.
Yeah, and because it's not getting a new one, it's staying positive to neutral all times.
Mm-hmm. And it's coming back because of the charge on this. It has a 1 + 1 charge. That's why it comes back. That's what's pulling it back. And because the charge here is stronger, it's pulling this over here. So both of them is happening at the same time. So let me write it here. Up here would be IE. Well, when it comes to the hydrogen, hydrogen is going through the IE process. And oxygen is going through the EA process. Does that make sense?
So basically those elements that are ionic with a stronger pull are always going into a EA phase. And those who are giving up are always going to an IA stage.
IEA stage, yes.
Yes.
Say that again.
Basically, let's say like previous example, like David said, Na and Cl. Since Cl was 17, it's going on the EA stage because it's a stronger pull.
Got it.
And Na, because it's a 11 charge, is a IA stage. It's giving off. It's giving away an electron.
Okay.
IE, yeah.
Yeah.
It's an IE stage when it's giving off the electrons, and the one gaining is going through the EA phase.
Yep, yes, exactly. These are just phases. Exactly.
Okay.
That's how he wants you to understand it. Just to understand it as phases. There's not a formula or anything like that. It's what's happening in the atomic level, the function, AP of electrons and atoms. You get it, Elmani?
Yes, thank you.
All right. Hope, do you understand? All right, so that's pretty much chapter 8. That's all there is to chapter 8, just those two things.
Yeah.
It's not big
He
much.
put, yeah, he just put 8.1 and 8.2, but that's basically just a periodic table how it functions. What we've been learning about the S's and the P's.
Yes, it's pretty much how it looks like in a periodic table, the SPs and stuff like that.
I'm gonna post something in the chat. Maybe it will help others.
So basically what we're learning now is the intro to Lewis dot structures when it comes to the electrons. This is just like, how do I say this? A descriptive form of doing chemistry instead of actually mixing with the chemicals. This is just like how it looks through text.
Okay, I think I got this. Let me see.
So I want to.
I hope he gives us a periodic table, like.
Or you can just bring yours.
I just posted one in WhatsApp group. I don't know if you guys see it.
Yeah, I got it. Oh, it has the spins, the nuts, the orbitals.
Mm-hmm. All right, so I want you to see this on a periodic table. Now that you guys understand this, I want to show you a periodic table. Let me see if I can. Give me a second. I'm trying to pull up the image. Okay. How am I going to? Oh, I have the picture saved. I think. Because I want to show you how it looks like on the periodic table. How electronic affinity and ionization looks, how it's happening on the table. So I'm trying to get the picture. Okay, I don't have the table. Sorry, give me a second. I'm still loading over here. Perfect image. This is what I want to show you. This. So just so you know, electron affinity and ionization energy looks the same on the periodic table. I'm going to share you guys my screen so you guys can see what I'm talking about.
Sorry, I stepped away to print that review sheet.
Do you guys see this?
Mm-hmm.
So as you see on the periodic table, the electron affinity increases when it goes up and when it goes to the right.
Because the stronger elements are on the bottom.
No. It increases because of the how stronger the element is. How do I explain this?
Because the stronger elements are in the bottom. They said like, how can I get you? Like FR 87. FR 87 has 87, 87. So the more you take away, basically it's going to your, because you're taking away going upwards, more positive, but you're giving away, so it's going to the right.
Because when you go to the right, you become more negative. When you go to the
Yeah,
left, you
becomes
become
more
more
negative.
positive.
More positive.
Right. And then when you go up the scale, it's
It's like you climbing up the ladder.
It will be easier to give off electricity. It will give more electrons is released the higher you go on the when you go up on the periodic table. So going up, when you go up on the periodic table, you give off more electrons. When you go this way to the periodic table, you're going across, you're getting more negative. You're receiving more negative. So all the elements on this side receive more negative than this side. And when you go up, I just said it and I just forgot. When you go up, you're I just had it and I forgot it. The more electrons you give off, the weaker the electron activity the easier it is to give off the electron. That's what I mean. So when you go up, you give off the electron easier than you do from the bottom, and when you go across, you get more negative.
Got it.
So right here, FR, it gives off it would give away its electron, but you need more power to get it to remove it because of the protons. While over here, hydrogen, you only have a charge of 1 proton, it's easier to give off the electron. And when you go across, you see you get more electrons, so you get more negative. Helium has 1, hydrogen has 1, helium has 2 electrons, so it's more negative than hydrogen. In the sense that it's more negative in the sense that it has more electrons. It's neutral, but it has more electrons. That's why it's more negative. That's what it means. How much more negative energy you can receive. Absorb on the right, give off on the left. Weaker as you go up, stronger as you go down. So that's electron affinity. Ionization energy is the same thing. It's the same thing as well. It's weaker to remove an electron, and on this side, it's stronger to receive an electron. It's stronger to remove an electron on this side, on ionization energy. Helium, you need more energy to remove the electron of helium than you do with hydrogen. And on electron affinity, with helium, it will receive more electrons than you will with hydrogen. One is receiving, one is giving. So ionization is endothermic, and electron affinity is exothermic. Does that make sense?
Yes.
Yes.
Can you repeat that?
Ionization energy is endothermic.
Oh, okay.
Electron affinity is exothermic.
All right. Thank you.
So I'm gonna throw you some questions. Chlorine. Is it stronger than Na or weaker than Na when it comes to giving off electrons?
Stronger.
Stronger.
Chlorine is stronger to give off electrons?
Yes.
No, it's not. Na is stronger to give off electrons.
Oh, to get, yes, to give.
Remove.
What?
You mean to remove or what?
Yeah, to remove. To remove electrons.
Because on the right side, they have more pros, like it's
Yeah.
gonna absorb them, right?
Mm-hmm. Yep. So to remove electron, you need more energy on chlorine to remove electron than you do for Na. So that's why it's easier to remove electrons on Na than it is on chlorine. Now, which one will receive better, which one will receive electrons? The K or the Ca? Which one will receive it easier?
The Ca.
Ca, right? So if I got neon and I got beryllium, who will receive and who will give off?
Neon will receive.
Beryllium will give off.
Right.
So beryllium will go through IE phase and neon will go through the EA phase.
Correct. So remember the periodic, remember the element that we talked about? Hydrogen and oxygen, water. Hydrogen is on which side?
The
Left side.
On the left. So that means it's doing what?
Giving off.
giving off,
And oxygen is what it's doing?
receiving, absorbing.
Receiving. It's on the right, exactly. So as I show you in the image, hydrogen was giving off to oxygen. Oxygen was also giving off, but because the energy is so low, it only gave up one electron to go back to hydrogen to create that bond. But yes, oxygen will receive it more than what hydrogen will. What about sodium and lithium? Which is stronger?
They're neutral. They're not neutral, they would stay the same.
You said sodium and which one?
Sodium and lithium. Which is stronger to give off an electron?
They're the same.
Mm-mm.
Na is stronger.
Mm-mm. Lithium is stronger to give off an electron.
But I thought Na has 11 and lithium has 3.
Right. So what does that tell you?
Oh, yeah. So the one with least is stronger to give off.
Exactly. Lithium has less electron energy than Na does.
Yes, because it's closer to the. Got it. Thank
So
you.
it's stronger.
It's
It's stronger.
It's closer.
That's
to
why
the
it's
proton.
closer to them. It's closer to the center than Na is.
Yes.
Now what about here? Argon and neon. Who is stronger?
Na.
And he is stronger to what?
Oh.
Because
And he is stronger to what?
To absorb.
And he is stronger to absorb.
Mhm.
Okay, so if I have aluminum and nitrogen, who's going to give off energy?
Aluminum.
Aluminum, right? Aluminum will give off energy. And neon would, and nitrogen would do what?
Receive.
It will receive it, exactly. Yep.
Hey, baby.
What's stronger? Aluminum or nitrogen?
Aluminum.
What's stronger?
Aluminum?
Nope.
Mm.
Look at the arrow. When you go up, it gets stronger.
Oh, true. Nitrogen. Okay, got it.
So it's the same thing, electron affinity, ionization energy, same arrows going across. It's just that one is giving off and the other one is receiving. And they both do the same thing. You see the arrows? They increase as you go this way.
Mm-hmm.
All right, so I guess that covers chapter 8. What do you guys want to cover now?
I had a question. I think, hold on. Can you just remind me what he meant, what the exception to the octet rule?
I haven't got that part yet done. I'm working on that right now.
Okay. And
I can do the start structures and the ionization.
the orbital symmetry, he has 50% and 100% filled suborbitals are most stable.
The Hund's rule.
Yeah, can we go over that?
That's Hund's rule. Right. All right. Let me pull up my review because I have
Unless
it.
somebody has to go over something else.
I'm good with that.
Yeah.
All right. So do you know what Hund's rule is? Everyone know the rules for Hund's?
Yeah, actually, hold on, I had some notes.
Yes.
Mm,
What's the definition of Hund's rule?
Hold on, I went to get my notes.
1 second.
The shells fill in order before they double. I think.
The no to. Is it the no to electrons in the same atom can have for quantum atoms?
Nobody?
So Hund's rule states that the most stable arrangement of electrons in subshells is the one with the greatest number of parallel spins.
So in other words, that's the definition, but in simplified form, other words, what does that mean?
Shells fill in order before they double.
Close, but no, not exactly.
It must have different contact numbers.
I'm gonna give you, it has 2 rules. So this is the first rule, which we're going over right now.
Sorry.
Yeah, it is. Okay, so it says, how I simplified it is each element is allowed one max spin.
Mm.
That's the first rule. Here's the second rule, which Johnny was saying, orbital symmetry. So that's Hund's rule. Each element is allowed one max spin. And we went over this yesterday, Henderson, in the end.
Yeah, that's what I just said.
And the orbital symmetry. This rule is used not too much because it really affects mostly the bigger ones. And so from what he taught us, there's two of them that affects this: chromium and copper. But before I touch those, let me go back to this, because before we continue on to Hund's rule, I want to know if everyone knows their quantum numbers, because it has to do with quantum numbers. So what are the quantum numbers again?
The N, L, ML, and MS.
Mm-hmm. Those are the quantum numbers, N, L, ML, MS. What is N again?
The principal quantum number.
Or
Shit. Hold on. Oh my gosh.
What was their question again? Sorry.
what is N for quantum number?
Number one?
N.
Is the principal something?
It's the principal quantum number, but in other words, what is it?
Oh, the number of shell?
It determines the energy.
You're close, Elmani.
Cat,
Go there. Go there. Is it the orbital?
No.
Mm.
The distance between electrons.
You guys forgot already?
I'm like trying to remember what it was, and I thought I wrote it down, and I.
Why can't I write this number? Oh my God, I just want to write this number. There you go.
All right, we give up. What is it?
The shell level.
Okay. And I have categorized the shell level.
Yes,
Okay.
the shell level.
Mm.
This shell here is N1. This shell here is N2, and this shell here is N3.
All right.
That's the N. What are the L's? What is the L?
The
It tells you
L is
what
angular.
orbital space is in.
So that's the
It tells you what orbital space is in.
Right. Tells you what, or it tells you what?
The
And
orbital shape.
Orbital shape, or in other words, simplified is. That's the definition, right? But what's the simplified?
It tells you in what orbital space is in. The name of the orbitals.
Name of the orbital, yeah. Orbital types, which are?
0 is in S, L, and 1 is in P. L2 is in D, L3 is in F, L4 is in G. Well, I know we're not gonna go over that, so we did
Yes.
not talk about it.
These are the orbital types, S, P, D, F. S would be in here. P, D, and F will be on the outside with the, with the outer shell. This will be N4. Why are you doing that? Does that make sense?
Yes.
Okay. So Henderson, I know you got this down packed. So let me give this to you. What is L for? What type is it?
L4 is in G.
Try again.
You talk about the name of the orbital?
Oh wait, L4? Yeah. Sorry.
Yeah.
Is the G.
Damn, that was a 3-pointer.
G type. What is L2?
It's a D type.
D type.
I mean P.
P type.
It's D type.
D type.
D type is L3.
L3 is F type.
Yeah, L3 is F type.
L0 is S. L1 is P type.
Wait, so someone's giving me wrong answers. Hold on. Yeah, confusing me now.
L0 is in S, L1 is in P, L2 is in D, L3 is in F, L4 is in G.
So let me write it in the chart. L0, right here, L0 is S.
S.
L1
L1.
is P. L2 is D. L3 is F. L4 is G. Did we went with H? No, right?
No.
But that'll be L5, right? L5 is H.
Yeah, I don't think he'll go that far.
He won't go that high, but that's pretty much, you get the idea.
Yep.
So those are the L's. Okay. So I'm just trying to see if you guys remember this, right? That how the quantum numbers are. And how many does the S-type have? So when it comes to ML, how many does the S-type have? How many momentum does it have?
0 or 1. Hold on. ML for S, it's 0.
Yep, 0. And P, how many?
P would be 1.
Nope. How many
Plus-
magnetic does it have?
plus
How many magnetic
1,
orbital?
0, -1.
How many is that?
Oh, 3.
3.
3.
And D?
D is 5.
Mm-hmm.
F
And
is
F?
7.
7. Yep. And from there on, that's when I ask you, what are they? For P, what are they?
It's 0, -1, 0, 1.
Mm-hmm. D would be?
+1. You have -1 already. D would be -2, -1, 0, 1, and 2.
Mm-hmm. And F would be?
-3, -2, -1, 0, 1, 2, 3.
Mm-hmm. -3, 2, 1, 0, 3, 1, 2, 3. And that equals to 7, that equals to 5, and this equals to 3.
Like ML for S-type is 1.
What?
ML for S-type is 1, right?
No. For the S, there's nothing. It's always 0.
I see on the last review he did, he put 1.
For S?
Yes.
Unless you're talking about the L.
Yes, I'm talking about the L.
Yeah, L will be 1.
Okay.
Yeah, L will be 1, but this is ML.
Like for P, you put L, you put L. You put MS for the P, you put 3.
For L, it would be L2.
No, I'm
No, wait,
talking
sorry,
about
L1.
the P type.
Yeah, that's L is 1. L1 is P-type. Where did I confuse you?
So, and the P, like for ML and P type, you put 3. It's supposed
Right.
to be -1, 0, +1.
No, you're confusing yourself. This is how many you have in there. There's 3 of them, which is -1, 0, and 1.
That's what I'm saying. And the
Right.
last two for the S type, ML, he put 0. For L, he put 1. Not L, MS, he put 1. So for the P type, ML, he put -1, 0, +1. And for the MS, he put 3. You see what I'm saying?
No. No.
I got a picture for the last review he did, like he did like that.
Okay. But I don't understand where you're confused.
Yeah, I'm trying to follow because I wrote down same thing. I had 0357 for SPD and F. You're saying for P, he put what?
For P type, for ML, he put -1, 0, +1. And for MS, he put 3.
For MS?
Yes.
What is MS?
What is MS?
For the last thing, I don't remember.
What is
MS
MS?
is just
MS is the spin, but MS would only be -half or +half.
Yeah, that's MS.
Send the picture in the chat so we can try to clarify it.
Yeah.
Okay. Let me send you the picture. Wait a second.
Because MS is just the spin on how it's spinning, which goes back to the Hund's rule.
Wait a second on my phone. Baby, do you see my phone? I can find my phone. Okay, I got it. I'll send you the picture. Sorry, guys.
It's okay.
No worries, this is why we're here. Maybe I did something wrong.
So I sent it. You see?
Okay. My thing wanted to freeze. Give me a second. Where do you see MS?
Not MS. Like, look for the S type. ML, that you put 0, and after that you put 1.
Right.
And
That's
for
one
the P
S.
type,
That's one S.
and for the P type, -1, 0, 1, and 3.
Oh, I see what she's talking about, but that's L and L1. It falls in the P type, but still gives you 3. -1, 0, and 1. That's what you're talking about?
Yeah,
Yeah,
but
that's what you're talking about.
it's still L1. It still is falling to P. That's what you're talking about, right, David?
Look for the first.
Yeah, the professor combined it. That's what it looks like. He combined it all in one, where David's charts are separate.
Oh,
So
okay.
if you look where see under L, it has zero.
Yeah, he just combined it.
Yeah, if you look L, below L, he has 0 and then an S, which is basically what David's chart said before. L equals 0. L 0 equals S. Then he has under ML, he has 0.
You will find that in 1S. That's what he
Right.
means. You will find it in 1S. It's not
Oh.
one that you don't write. Okay, so I guess you don't know how to write the quantum numbers. That's not how you write the quantum numbers.
Okay.
Quantum numbers is how you write it like this. Me and Henderson were doing yesterday. So again, we still goes to Hans' rule because now we're about to catch up on what I'm trying to tell you. So you're just jumping ahead. Wait for me, Almani. Wait for me. You're jumping ahead.
It's okay.
So right now, let's write. So you guys know the quantum numbers N, L, and all that stuff. So now we're gonna write it for each orbital type. I'm gonna type this one up because I can't do this thing. So for the S type and how you write it for the quantum numbers is this. That's how you write the quantum number for the S types. This here is the N, this is the L, this is the ML, and this is the MS. As Hans' rule, they each allowed just one max spin. The max spin is this. And as Pauli's rule, remember Pauli's rule? Pauli exclusion?
No, it can be for the same. One must be different. All quantum numbers cannot be the same.
Mm-hmm. So they're all not the same, but at the same time, it's only allowed one spin. So this here is one spin, and this here is another spin. So that's the rules for Hans' rule. The S type, that's how it would look. For P, it gets bigger. For D, it gets bigger, and F, it gets bigger. But that's how you write the quantum numbers for the S types. You want me to put how to write it for the P types?
Yes, please.
That's P.
You think he would ask us to write it out this way?
Not this way, but he's going to give you an element and ask you to do that.
Actually, he does on the review sheet on the back. He has it. You have to break it up apart.
Oh, you do? Okay, so yeah.
Yeah. On the furthest back, It says you have
Oh, I
to.
didn't see that part, so I guess I missed
You,
that part.
it says two electrons in the force S suborbitals. Basically, how you went over it. It said
Mhm.
E1, E2, and then you have to like break it apart to show if Pauli exclusion doesn't work out or not.
The last page you said? Let me see.
Let me see.
Yeah, it's like the second to last page. It's like it's
I
in
love how this thing
page
freezes.
4. It's on top. It's underneath Pauli exclusion principle. It's in the bottom. It's in the by the electron configuration page, all the way in the bottom.
Oh, consider 2 electrons in the 4s orbital. Okay, I see how it is. So
So can
basically,
we do this?
yeah, basically what me and Henderson were doing yesterday and towards the end. All right, so I can do that.
Yeah, exactly. Yes, yes.
Yeah, we can do that.
And also, some of us, some of the group members are here, were at the school. I went over chapter 7 about the frequency and wavelength. He has that too in there. So
Yeah, he wants us to do something extra with it as well. So I'm gonna add some. You know how I taught you the number for C is like 3 times 10 to the 8th power?
yeah, yeah.
That's for nanometers, and the one he gave us is for centimeters.
Got it.
Wait, what did
So
he?
we had to convert it not to nanometer. We had to convert it to centimeters.
I mean, if you get, that's what I said. I wanted to. That's the extra stuff I need to add to the review. That's if you get a problem that's asking you how to
How to convert it to centimeters.
right. I mean, how to convert it to
So
meters. Yeah.
exactly.
So if they give you a wave, like if you give you a wave of frequency, whatever, and it says, oh, it's this much centimeters, you have to change it to meters.
So basically, we need to learn the conversion of centimeter, the formula of that to convert it to.
Mm-hmm. So that's the P type. D is worse. You guys ready to see D? That's D. As you can see, for Pauli's principle, none of them are the same. They're all different. Those are the combinations that you'll write it with.
Hold on 1 second. Okay.
All right, so I'm just gonna go with D because the F is worse. It's just more.
Yeah.
F is just more. It's the same concept, it's more. So as you see, do you guys see anything right now? Anything sticks out?
Yes.
What sticks out?
The MLs are changing. on the d orbitals.
The ML, you mean this?
Yes.
They're also changing here as well. Oh, I forgot to put a 1, but yeah, that's supposed to be a 1. A little typo here is supposed to be a 1. Yeah, it's supposed to be a 1. Sorry. Typo error right there.
So 2, 1, 1, or 2, -1 and 1.
No, it's 2, 1, 1 with a negative half.
Okay.
It's like the electronic configuration, but this time we're just doing the quantum numbers. So no one sees what I'm talking about, right?
No.
All right, here's a hint. Spin for the S type. How many spins does it have?
1.
Check again.
2.
2. 2 spins. But 1 is what?
Positive, 1 negative.
1 is negative,
1.
exactly. And the P?
Same.
Has 6 in total.
Wait, how's it 6?
I get what you're saying. 'Cause you
3 positive,
have 3 positive, 3 negative.
3 negative.
Oh,
I meant to write 3, not 6. And D?
You have 10.
10. Right. 5 positive, 5 negative. This will come in handy. Just remember this part. This will come in handy and you see why. All right, can I move on?
yes.
Okay, so moving on to the electronic configuration. So that means in each orbital, S-type will have a total of 2 electrons in that orbital. P-types will have a total of 6 electrons, and F-types will have a total of 14 electrons. And D will have 10. Yes, what you saw, the positive and negative spins. So going up to catching up to what we're doing now, the Hund's rule is based off this symbol. And I'm about to type it up right now. The spin charge. So when they mean by max spin, it's the spin charge. This symbol equals the sum of the spin. And you'll see what I'm talking about when I start going on here. So we're gonna do right now hydrogen.
Oh, I remember he did this with that symbol.
So let's do hydrogen. Gonna start one at a time right now. Hydrogen. What is the electronic configuration of hydrogen?
One S1.
This one.
1s1, right? How will we write this in quantum number?
We put 1, comma 0, comma 0, plus 1/2.
That's how you write the quantum number for hydrogen. And let me rewrite this part here. I'm gonna rewrite this. So with the quantum number, hold on. Okay, so let me just put it down here. There you go.
Mommy. Yes, baby. Why?
Do you understand this or no? Or do you want me to go over it? You understand it?
Yes.
All right. So now we're gonna do the next element. He. What will be the electronic configuration?
One S2.
1s2. How will we write this in quantum number? I know you know this, Henderson. Give this someone else a chance.
I'm not gonna say anything.
Can I try?
Go for it.
Okay. 1 0 0 negative 1/2.
But wait, why are we doing negative 1/2? Even though you're correct, but why?
Because it's filling the shell.
Yes, and
I don't know.
You got this, Hope.
It's
What's
the rule.
what's the rule? What's the rule? Each element is allowed one max spin.
Yeah.
So, because H is already holding the plus one.
Right.
That's already its max. So this is already used. We can't use this anymore. So now the next element is this. It has to be that. This part here alternates.
So because hydrogen alone would be a plus spin, a positive spin, the element that it's like combined now for helium, it's negative.
It will be, the thing is not no, the element is not negative. I'll show you what's the charge. I'm not talking about the charge. I'm talking about the spin on the quantum number. Because this is already occupied, we cannot write this anymore. The rule says each element is allowed one max spin, and that's their max spin is positive. And the rule for Pauli is no two electrons in the same atom can have the same set of 4 quantum numbers. So we cannot write this again.
Okay.
So you have to write it like this.
I think I need a few more examples of these.
All right, so here comes the part where it will all make sense when it comes to the charge. I'm just going to rewrite this in a much neater way.
New studies available on prolific.
There you go. Electronic configuration, 1s2. This here it's from okay, so let me show you another one. Oops. Okay, let me show you how it looks like here. So let me give me this thing. For hydrogen, the spin was like this. That was a spin for hydrogen. For helium, because it is 1s1. So for helium, it's 1s2. So the spin is 1, 2. And because it's the S type, how many electrons can be in the S?
2.
2. So when you're filling it up, it's a plus. And by the time it gets full, it becomes a negative. So I'm going to continue on with all the elements and it will all make sense. It will all make sense in the end.
Yes, it does.
It will all make sense in the end. In the beginning, it's a little confusing, but you'll see. It will make sense in the end. So I'm going to move on. Lithium. What's the configuration?
1s2.
1s2.
2s1.
2s1. What's the quantum numbers?
1.
What?
1.
Nope. What shell are we on?
Oh, that's yeah.
Yes,
2.
The second shell.
Yeah.
What type is it?
S type.
Which is?
0.
0. And does he have anything extra for 0 for the ML?
No.
0.
Oh.
And now that we're starting a new shell, it's going to be a plus. That's the
Okay.
quantum number. So this means this here is this. Going up, going down, going up. This shell is done. New shell. Well, not really new shell, but orbit pretty much. Sorry, orbit. This shell is done, but in this shell, there's the S orbit. It's starting with this. We're starting the new orbit in the shell. So that's lithium. So when you're doing the quantum numbers, it focuses on the last shell on the electronic configuration for quantum numbers. This is it right here. Hold on, let me erase that. So this is how it will get this charge. From the 1s2, we have it here. Plus upspin plus downspin, they equal 0. Plus the upspin, the charge will be 0.5. As you see, it's still following the rule. It's only allowed one max spin. The max spin it can hold is 0.5. Another element that has the same spin, same charge is H. Remember hydrogen? It's 1s1. Quantum number 1, 0, 0, half. This one 2, 0, 0, 1 half. Difference, this one only has one shell. This one has 2. You want to see it visually? I'm going to show you. That's lithium, 2 shells. Hydrogen, 1 shell. So because it's 1 shell and 1, and because it's on the second shell and 2, The orbital type is the S. And we know S is 0, L0. And when L is 0, ML, is also 0. And remember, the spin alternates. So you start with positive and then you go with negative, then you go positive and negative. But that only happens when you're going to fill up the shell, when the shell is going to get full. So far, the S is what? The S orbital is what? We have 1 in the S orbital and we need 2. So it's half full. The orbit is half full. So that means this is a plus. So the next part is going to be a negative. So I'm going to write the next one and you'll see. What's the next element?
Sodium.
We're going to element number 4.
Sorry. You did lithium just now, so beryllium.
Beryllium. The configuration.
1s2,
1s,
2s2.
2.
So 2s2, what does that mean? What does that mean for the S? For the S orbit?
Is 0.
It's full. So how do we write the configuration on this one? What shell is on?
2.
Orbit.
S. 0.
And does it have any magnetism, whatever it's called, a magnet? What's the word? I forgot the name. The magnetic quantum number. What's the magnetic?
Is 0.
0. And the spin?
Minus.
Minus half. That's the quantum number for beryllium.
So this is how he may give you just beryllium and say, what's the quantum number? Possible.
So what would the charge be?
The electronic configuration. What do you mean?
Charge spin for beryllium.
1/2 spin.
0.5.
Ay. I'm trying to center it. Yeah, let's see if you can see it. But can you see it? Your charge is 0. In the first shell,
The first shell canceled out.
because it had an up and it had a down. Now we're doing is the same thing again, the S orbital. Now we're going for the second shell, S orbit, same thing. Started with an up, and now got full. And went down. So these become 0. This becomes 0. 0 plus 0 is 0. The spin is 0.
So basically they're canceling each other out
Mm-hmm.
if they have a full spin.
Mm-hmm.
Otherwise, the answer is going to be either plus or minus 0.5.
You'll see. You'll see. You'll see. You will see. But like I said, as I continue on, everything will make sense. So let me do the next element. What's the next element?
Boron.
I love how my mouse is so sensitive. Boron. Now we're touching on a new orbit. What's the electronic configuration?
So it would be 1s, 2,
Please. 2S,
2p.
1S2, 2S2, 2P1. That's why. Right, that's it.
2p1. Now we're touching on a new orbit, the p orbits. So what will be the configuration? The quantum numbers. What shell are we still on?
We're on 2.
2.
We're still on the second shell, right? Now what orbit are we touching?
1.
P.
P, which is
1.
1, right? And now remember the P breaks up into 3. You can be negative P, P0, or P1. So we are going to start with the negative P. So we will write it as -1. In the spin, we're starting. So what are we doing? When we start, what it becomes what?
Positive.
Positive.
Why is it -1?
How many, remember in the chart that I gave you, how many spins does it have?
0.5.
The P has 6 spins, 3 positive and 3 negative. So to differentiate the 3 types, we write it as, you can write it as X, Y, Z, or -1, 0, 1.
So for the quantum, you wouldn't have -1, 0, and 1. You would just put the first one.
For the quantum, we'll read that question.
So like if P could be -1, 0, or 1, you don't have to put that in the quantum numbers.
You can use either one. You can use -1, you can use 0, or you can use 1, as long as you understand it.
Oh, so any of them would be correct?
Yes.
Yeah, I think that was Hope's question, because if P can be -1, 0, or 1, why do we put the -1?
Yeah.
I think it's easier to start with the negative.
Okay.
Yeah, like, okay, that was fine. Okay. Question answered.
But we don't have to include all.
You're jumping ahead.
Oh, sorry. Okay.
Yeah, I
It's
thought
just-
you had to include all, so that's why I was a little confused.
Okay, so yeah, you're jumping ahead. You're jumping ahead. But yeah, this is how you write this. That's the quantum number. And what would the charge be? The spin charge.
0.5.
The spin charge
0.5.
0.
Just 0.5, yeah.
Oh, 0.5.
Yep, because look, in this shell,
Oh, we only did one, 1, 2.
this orbit is full. So now we're starting a new orbit and it has a plus spin. So in other words, I'm going to rewrite this over because I already have it here. Do you see it?
Mm-hmm. I see it now. So this cancel, the first part canceled, the second part canceled, leaving you with a positive 5. Positive
Right.
5.
Because remember, beryllium was just this. Oh my God, beryllium was just this. The rule says maximum spin. You can't put a positive here. Only a negative. That's how the rules make sense when you write it out like that. So I'm going to continue on to the next element. My friend's favorite, carbon.
Mm-hmm.
Now what's the configuration?
One S2, 2S2, and 2P.
Break up the P's. Don't put them all together. Break them up.
2P1, 2P1 again.
2P1, 2P1.
That's it, I think.
Now here comes the fun part. What is the quantum numbers?
So it's 2 shells.
Shell 2, yeah.
L2 would be
In what orbit did the electron land?
in the P
What's P?
is 3. P is 3.
1.
1. And since you already used -1 on the last element, now all we have left is 0 and 1. So I'm going to use 0. And the spin, what are we still doing?
Still positive.
It's still positive because it's still adding. We're not full yet, we're half full.
That's a +1 charge.
And it will have a +1 charge, correct. So let me show you. Let me rewrite this and how I have it here, nice and neat. Questions?
So on this one, it doesn't cancel out at the end because it's too positive. That's why you're adding them.
Mm-hmm.
Would he ask us to do this total spin charge that way? Or no?
I hope not.
I know. I mean, it helps with getting
Yeah.
the spin, but
Yeah.
Because
I don't know if I can do it alone.
I don't think he is, but just know it just in case. Because it says
Yeah.
here, he is covering up on that. He just says the first are identical, so they must differ in spin number. And since there are only 2 ms values, that is the max number of electrons in the orbital. But I don't see any other questions pertaining to that. But but this sum is what helps understand Hund's rule. He wrote it differently. He wrote degenerate orbital groups fall 1 and 1 before they double up.
yeah.
Which equals the rate of max spin. So what I'm teaching you right now.
So the rate of max spin is this on the bottom. This
Is
sum.
1. Is the 1, yeah.
Okay.
So the 50 will be the 0.5, the 1 will be 100.
So in this case, how did I write it here? Let me see, hold on. I wrote it here how it became, what is the percentage? Okay, so in this case, we're going to be focusing on this section here, because this here is just the core. So we're not worried about that. We're just going to be worried about the valence, which is that. So when it comes to orbital symmetry, the S is full, so it is 100%. The P's, there's 6 of them, right? So out of the 6, only 2 are full. Only 2 of them we only have 2 electrons in the P out of the 6. So the percentage of this would be like what? 30%, 33? 33.3333%.
Yeah.
But this orbital symmetry really just affects the bigger ones, not these. But it does, in a way, make sense as symmetry because there's one here and there's one here.
So all right, I'm not understanding how. What's he, so when he's gonna ask orbital symmetry 50% to 100? I don't understand that.
I don't think he's gonna ask that because that's math. That's just involving math.
I mean, but he specified 50% and 100% on this review sheet.
It says filled suborbitals are the most stable. 50% and 100%. So when we have 100% here, I guess he means is more stable. This is more stable.
Then versus a 50% filled.
Mm-hmm. But I'll touch on that one on the elements that he wants us to, that really affects us. It doesn't affect these. That's the thing. It doesn't affect these. It affects the two that he specifically went over in class.
Which are
The
Chromium
fluorine.
and chromium and copper.
okay.
I just want you to understand the charge, the configuration, how the Hund's rule works with the first 10 elements. All right. So I'm gonna go to the next one.
God
Next
bless
up.
David.
Huh?
I said, God bless your heart, David.
Oh, thanks. My mom said the same thing. When I told her what I'm doing, she said the same thing. So I'm gonna go to the next one, the next element. Where am I? Okay, the next element we're doing is oxygen. No, it's nitrogen. What's the electronic configuration?
One S2. 2S2. 2P. Wait.
You're good. Keep going.
Oh, is it?
Yeah.
Three.
No, we're not stacking them yet.
Wait. Oh, wait. We can't do that. So it'd be two. Wait.
There's no stacking until we get to 6.
So it'd be.
Quantum number?
Would be 2.
1.
This is what's nice about having a bus truck, is you don't gotta go around things, you just go over things. The hunters are gonna be next. We're gonna get these boaters. The hunters are on the front. We're gonna get these boaters.
MS? You mean the ML?
0.
The magnet? You already use 0.
1.
How about we just start really ready? They're not even they can't jump in their vehicle and leave. We're gonna go, but splash them all. Budman, I'm so mad at you, Budman. You know better than this, Budman. You know better than coming out here. This is not your lake. And when you look at, are you bringing your baby?
Plus half.
Oh, she's trying to pick her nose. You have a booger? All right. Yeah, get the booger. Budman, you're showing over.
Yep.
You can't be in this boat. Guys, this isn't your lake. You gotta leave. Please, yeah. Look your boat here. I'll strap it down for you. Boom. It's just
Stop smiling.
It's not smiling. Yup.
This is serious.
Before I write down the whole thing, can anyone take a guess of what the charge would be? Oops.
One 1.5.
1.5.
1.5.
Questions?
Yeah, so why do you write it out like 2p1, 2p1, 2p1?
Before you need, there's 6 of them, so we need 3 positive and 3 negative. The first part gets full with positive. That's the pattern. It was the same way with the S. What's the first thing we did when we started the orbital? It starts with a positive, and then it gets full. It ended up with a negative. The next orbit started with a positive. To get it full, the next one's going to be a negative. The rule: each is allowed 1 spin. Pauli's rule: no electrons in the same atom can have the same 4 quantum numbers.
Okay.
And he told us we couldn't stack unless it was 5
Unless,
or
to me, like to write 2p7 or stuff like that.
yeah.
Yeah, until we get all 1s, and then we can start stacking up to 2 and all that other stuff. But sorry. When do you write to 2p6, 2p7? That's like on bigger elements. That's when he wants you to write that. After you do 2p1, 2, 3, and 4, 5. After 5, then that's when you write all accumulated. Questions? I'm already here. So what are the 3 ones that we just did? We did beryllium, right? We did carbon, and now we just did nitrogen. What was the quantum number for sorry, not beryllium, carbon? Wait, what? I'm confused. And carbon. Yeah. Boron. What was the quantum number for boron?
One
Two.
S 2.
2,
Oh, sorry. 2, 1.
1,
0, 0. I mean 0.
you want to use 0? Okay. 0
Plus 1/2.
plus 1/2.
Let's use 1. Sorry. Let's use 1.
You want to use 1?
Yeah.
Okay.
So let's check on 1. Yeah.
All right. So for carbon, what was the carbon?
Two,
2,
1,
1,
0,
0
plus half.
plus half. And we just did nitrogen.
2,
2, 1.
1.
It's 1 and 0 already used. All we left is -1
Yes.
plus 1/2. That's the rule. Hund's rule, Pauli's rule, all together. This one has a 0.5 spin. This one has a 1 spin, and this one has a 1.5 spin. Does this help? Hope?
So as they go up, the spin increases? Or that's not factual? I'm just making an assumption on a pattern.
Basically, it cannot pass more than 2 because it's occupying 2. So it goes 2, 1. No, it goes 0.5, 1, 1.5, then 2, and then goes back down.
Until 3.
Okay. Now I'm gonna answer your question, Siljani, with this one. To answer your question, let's use the element oxygen. What's the configuration for oxygen?
One is 2.
1s2,
2s2,
2s2,
2p1,
2p what?
1.
No, they're all the 3 p's are full now.
2p2,
2p2,
2p1,
2p1,
2p1.
2p1. Each orbit can hold 2. Well, each part here holds 2.
Back hurts.
So anyone except Henderson, give me a guess on the quantum number for this.
2,
2,
1,
1. You can use any one.
oh, -1.
-1. And now what's this?
-half.
-1/2. When it starts to double, it becomes a negative. When it's singular, it's positive. That was the pattern. Let me show you in this image that I'm about to do right now. My God. That's what's happening with the spins. We can't, there is no extra P. Because remember, the thing was just 1, negative, plus, and 0. So let me write this. It was -1, 0, and 1. There is no extra P's. So then it's going to start, now it's going to start stacking, doubling. Remember the P's, it has 3 positive and 3 negatives, 6 in total. You already have 3 positive, now we just need the 3 negatives. That's the rule for the P. And how do we get the negative? By doubling up. The slot's already full. So P looks like this with the lines of 1, 2, 3, 4, 5, 6. This is full, and this is full. And now that this is full, we go back. Now we fill this up, then we fill this up, and then we fill this up. The pattern for S. 2S. 2 P's, all of that. Each orbit separately has 2. Combined, this would be 2p4. But he doesn't want you to write it like that. He wants you to write it like this. Questions?
I think I get it.
The last 2 should be easy because all we're doing is just filling up the rest of the orbit. So let me show you how I have it written here for this one. So Johnny, I mean, a wild guess what the spin would be. The oxygen.
I don't know, 1.5.
Hope. What's the spin for oxygen?
Oh, the MS, you mean?
What's
Like-
what's the total spin? The sum of the total spin.
-1/2.
Right.
Hayes, what's the spin? What's the total spin?
Oh, the total spin.
Yes.
Oh, so that would be 1.5.
Amani, what's the total spin?
1.
1.
Oh.
It's down here. As you see, it starts to get longer and longer. Does it make sense?
Yeah.
Questions? No questions. I'm going to move on to the next element. Next element, fluorine. Electronic configuration.
1s2. 2s2. 2p2. 2p2. 2p1.
Or the correct way is just this. But he doesn't want you to write it like this, but this is the correct way how you're supposed to write it.
2p5.
Mm-hmm.
Okay.
But he doesn't want you to write like that. He wants you to break it up because he wants to see that you understand that it doubles up before the next one. Before the next one.
Okay.
Okay, so give me the electronic configuration. I mean the quantum number.
2. 1. 0. Minus half.
The pattern repeats.
Yeah.
Henderson, what's the total sum?
0.5.
0.5. Total spin will be 0.5. But I have it written nice and neat, so I'm gonna rewrite this. This is why it's 0.5.
Milk. Where's milk? Milk? I want milk.
Go get it.
But I don't know how to make milk.
Questions? Is it starting to make sense now how it starts to fill up? And how the spins work?
Yes.
Yeah.
Because the first two element is a bit confusing, but as you continue on, that's how it happens. All right, the last one. Neon. This one we can write it in stack, but I'm gonna write it in triple. What's the configuration?
Two S1. One S1.
One S1.
One-
Wait,
One
what?
S2. One
One
S2.
S2.
Two S2. Two P6.
Right. But I want to split it up.
Oh, two P2. Two P2. Two P2.
That's when you write it in stack. When they're already all full, you start writing in stack. Does that make sense?
Yeah.
So what would be the spin, Sildrani? The spin charge, the spin total.
Sorry, I stepped away.
Remember the pattern.
So this would be, would it be half?
The spin. The total spin will be what?
0.5?
Look at it again.
So what? 1s, this is Kinsey, this is Kinsey.
When it's doubling, you're adding the negative. When it's singular, it's all positive. So they're all double. So you got one positive and one negative, one positive, one negative, one positive, one negative, one positive, one negative, and one positive, one negative. You add them all up, the spin charge would be, the total spin would be. You got this.
I'm stumped.
All right, I'm gonna write it out. This one's a bigger one, so. Okay, hold on. Erase this. Because this one's huge. Can you see it? This is neon.
Okay, so 0 because, like you said, 1 positive, 1 negative, 1 positive, they each canceled each other out. So
Mhm.
0 across the board.
So maybe if I write it like this. Does that make sense?
Yeah. 2.
Questions? So I have a question here. This is the last element on the periodic table on the second row, AKA second shell. What does that mean?
I didn't hear you. I lost audio. I can't hear.
Can you guys hear me now?
No, I
Okay, so this is the last element on the periodic table for the second level, second shell. What's happening? What does that mean?
It's full.
It's full. And we call this what? When it's full, what's the name of it?
Octet.
Who has a periodic table in front of them?
Yeah.
You have a periodic table in front of you, Henderson?
Yes.
All right, on the periodic table, which element are full? What are the elements that are full?
You have argon, krypton.
Helium.
Mhm. And the one we just did now.
Mhm.
Neon, argon, krypton, Xen. and Rn.
Right. Those are full.
So those are all octet.
Those are all octets. Yes. So going on the periodic table from B all the way down and B going to the right to neon, all of that, that's what block is that?
The P block?
The P block. The P block. See? What are the, you see the orbits that we're playing with? P. When we did beryllium, what block is it on?
S block.
The S block. And what was the configuration for that one?
One S2,
There you go.
2S, yeah. 2S1.
Beryllium.
Oh, okay. I thought you said Li.
You see, and it ends up in the S block.
Okay.
Now, the third row on the periodic table, what shell is that?
The D?
Shell.
Oh,
3.
Yep, that's the third shell. So that's the pattern as well. That's another pattern in the periodic table. First row, first shell. Second row, second shell. Third row, third shell. Fourth row, fourth shell, and so on. Fifth row, fifth shell. Sixth row, sixth shell. Seventh row, seventh shell. So let's move on to the fourth shell. But before I do that, question, do you guys know what abbreviation is?
Parenthesis
Yeah.
NE.
when you, like the shorthand, when you have to put in brackets the previous element? Is that what you're talking about?
Yes, but I wouldn't call it previous elements. So let's start simple. Let's start in the first, let's use the first two rows, the first row and the second row. What would be, you're using the octet as a core element. So what's the octet on the first row?
Helium?
Helium. So this is our core. This is our core for the
Oh, so it would
second
be the
row.
last full, like, element, the prior octet?
This is the core for our second row. So when we're writing lithium, you write He as our core, and the valence is going to be second shell, orbital S, 1 electron. It's setting it so because the core of this one is it's already 1s. It's just another way of writing 1s2.
Do you think he'll expect it this way?
Yes, because he gave us a question. He gave us questions to practice on with this.
Okay, I didn't.
So now that I'm jumping up to row number 4, it's going to be which shell?
4.
Shell 4, right. So now let's touch on the element that that affects the Hund's rule. Since you guys understand how the quantum thing, how the spins work. Do you guys understand the spins?
What you just did?
Yes.
Yeah.
Okay, so if it's an octet, what's a spin?
Would be 0.
0. So a quick thing to remember, at the ends on the right side, the octets, the spins is 0. On the left, the spins would be? It's the same as helium, so it would be
0.
0.5.
0.5.
Oh.
And the pattern repeats. 0.5, 0. 0.5, then it goes up to 0.5, 1, 1.5, then back to 1, then back to 0.5, and then 0. So the reason why I'm touching this one is because this one is a little tricky. That's why it affects this rule. Again, that's where the symmetry and everything comes about. So let's do chromium. That's the 24 elements. I'm gonna write it here. The 24th element. So what will be the electronic configuration? I don't want the long way because it's too much to write. So let's write the abbreviation. What would be our core?
Argon.
Argon. So right now we're not following Hund's rule. Let's fill it up the way we know it. How would you normally fill it up?
For S.
4S.
Yeah, but 2 of these layovers are 6 hours each.
Then go 2.
4S2. And where is it on the periodic table? Which block?
Is in the D block.
In the D block. So we're gonna be playing with the D orbitals.
So you're gonna go to 3D.
3D.
So you're gonna be 1, 2, 3, 4.
You want to do 1, 2, 3, 4?
No, 4. Can you just write 4?
No, he doesn't. Remember, we're not doing this yet.
So then we're gonna do like the P type. We're gonna go
Mhm.
3D1, 3D2. I mean 3D1, 3D1.
The 3D1, yep.
There you go. 3D1. Then 3D1.
That's how normally we will write it, right?
That's huh?
That's how normally we would write it.
That's how he wants it, yeah.
Don't mix it up. This is how normally we would write it. That's the correct way to write it. But we're doing the orbital symmetry. So right here, this is imbalanced. Because on this side, we have 100%.
And 4S.
And here we have only 40%.
Yeah.
So there's no symmetry here. This is how this rule comes into play with this. Can we tell? Well, you can check by doing the spin. What will be the spin total for this?
A spin of 0.
Look at the math.
0.5.
0.5 to 1.5.
I'm gonna write the key over here. When it's
This is
1,
1.
it's
This
0.5.
is
When
1.
it's 2, it's negative 0.5.
2.
Or in other words, 0. Yes, it will be 2. 0.5, 0.5, 0.5, 0.5. This is 0.5 plus and negative, so they cancel out, become a 0. Because there's a 2 here. So this is an imbalanced spin for this one, because we got 2. The spin is imbalanced. So the correct way for the rule this to work is that we have to change the numbers around. Another one gets added here, this becomes a 1 and this becomes a 1. And now there's a symmetry. This is half full, so it's 50%. This is also half full, 50%. And there's your symmetry. The spin will be different now. The spin has raised. Now what's the spin?
Okay, done.
2.5.
Check again.
A 1.5 spin.
Check again. When it's a 1, it's a 0.5. When it's a 2, it's a 0. Add them.
A 0.5 spin.
No, this is 0.5. 0.5. 0.5. Add them.
3.
3.
So basically, when you move to the d orbitals, you have to make it balanced, and then you have to count for 4s all the spins.
Yeah.
Okay.
The S was always included. It's just that the other one,
It was
it was a 2.
Exactly. Okay, got you.
So why 4S is only 1, not 4S2?
The balance, symmetry.
Because it's already balanced. So since we bumped it down to one of the 3D, it became unbalanced.
Before it was this. Before this was 100%. Because it was full with 2. And this one, for the d orbital to be full, you need 10 out of 10.
Oh, got it.
I didn't follow.
To equal 100%.
The balance threw me off. I don't
Well,
follow.
before we only had 4 of them. So it was 4 out of 10, which was only 40% of the orbit full. But that means there's no symmetry. You got 100% here and you got 40% here. There's no symmetry. And for it to become symmetry, you need at least 50 here, 50 here. But that goes on with the higher elements, which I don't think he's gonna go higher than, let me see what's how he went. He
He
did an
actually went
element,
up to 29.
yeah, to 29. That's how high as we can go. That's how high he's gonna go, I think. Yeah, 29, which is pretty much what the last thing he covered on class. That is copper. Copper has an exception for this one, but it's still somewhat symmetry. You want to see copper? Or you got questions?
This threw me off with the symmetry on these. I'll watch the next one and then I have to hop off.
You don't want to ask questions?
Was I on mute? Can you hear me?
Yeah, I can hear you.
Did you hear me before?
Yeah, you said it threw you off, but I don't know if you have questions.
No, so I said I'll watch the other to see if I'll grasp it with the next one.
Okay, so let's do copper.
Okay, and then I have to sign off for today.
Hope, do you understand it?
Yeah.
All right. So we're gonna do copper, which is Cu, and it's the 29 element. So Hope, give me the configuration for copper.
Argon.
1.
Don't give me the long version. Just give me the short version.
Oh, don't give you the long version.
No, that's too long. It's too long. It's too much to write.
Oh.
What's the core?
Oh, wait, so what, hold on.
You have the periodic table on you, right?
Yeah.
All right, we're on line number 4. So if you're on line number 4, what core do we use from line number 3?
Argon.
Exactly. So that's our core. All right, and then we continue on to writing it normal. How would we normally write this one? It's do you remember the order?
Yeah. But I don't know why all of a sudden I'm confused. How do, like, I don't know, my mind is like jumbled.
All right, so let me refresh you on the order. In N1, what's in there? What would we write in N1 in the first shell? What goes in the first shell? What orbits?
S.
S.
1s, right? Now for N2, what orbits are in here? Starts with 2
2s, 2p.
and
And then
2p.
2p.
So this is the order, the off-bow order, so for each shell. And 3,
S.
S.
and look at the periodic table. Jumps to what block?
D.
D.
Which one?
D.
I'm hearing 2 answers.
E like David?
No. You look at the P. It's on the P block. You see that big gap in the middle on the third line?
Where it goes from magnesium to Al.
Look at the third line. You see NaMg, and you see a whole gap, and then you see Al.
Oh, yeah.
Yeah, that's what I mean.
Oh.
I see now.
Now N3 and 4. This one has all of them. So this is where we're on now. It starts with 4s, and then what comes after that? What do you see on the periodic table? What's in the middle?
3D.
3d, and then it ends at
4P.
4p.
Yeah, and that's the off-bow order.
Okay.
And 5. Five S.
Four S.
No, we already did. 4s is on the fourth
Oh,
shell.
4D.
5.
4d and
5P.
5p, right? So with this order, how we do argon?
Let's see.
What do we start with?
Start with 4s2.
Mm-hmm.
And then
We're gonna break it up. So remember, the D has how many?
6.
-2, -1, 0, 1, 2.
What? Oh,
That's
that.
5. And
Pass 5. Another way to remember as well, which I was doing before, how many electrons are there? There are 29 electrons. So according to argon, I'm gonna get my table, hold on. According to argon, argon has 18 electrons. So there's already 18 here. All of these here will be the total, will sum up the total of 29. So you have 18 right now, 19, 20. We need 9 more. So let me erase this part here. It breaks up into 5. How will we fill it up? They each gets what?
Two.
They each gets 1, 1, 1, 1. So we have 18, 19, 20, 21, 22, 23, 24, 25. So we're already using 25 electrons. We have 4 more. Once each of them gets full, what happens next?
Double.
It starts to double, right? So now this becomes a 2. So that's 29, that's 25, 26, 27, 28, and 29.
Wait.
It's the same way, same thing how we did in P's. Now we're doing it in D. P was only 3. D is 5. Questions? No questions?
Nope.
No, I'm good.
No.
So according to copper, with the rules that we have right now, what's the percentage happening right here?
That's 100%. That's 2, 4, 6, 8. 85%. Not 2, 4, 6, 2.
9 out of 10.
But what makes the left side 100? Like why?
Because
Because
they're
only 9
already
slots
full.
full.
Because they're already full.
How many electrons can S have?
How many what?
How many electrons can the S orbital have?
Oh, only 2.
2. That's what makes it 100%.
Gotcha.
And the D, you need 10. Orbital has 10 slots.
So right now we have 90.
90%.
90% full.
There's no symmetry. So this is not technically, this is how
So we
you
have to. So we have to move the S.
Mhm.
To the D slot.
Correct. Here's a crazy thing about this. I was gonna say something. I forgot. All right, so we're gonna continue on. So yes, we have to move this over. This becomes a 1 and this becomes a 2. So now the new percentage is going to be 50%. And this was going to be 100%. This is allowed. It's allowed because I'm going to assume 50 is also a symmetry on its own, and 100% is a symmetry on its own. So that's what it says, with the exception of copper.
Okay, so everything else has to be 100 except for copper? Is that what you mean?
Yeah. No,
Oh,
just copper and chromium are the only two that you need to remember that have this, that this rule really affects for symmetry. Questions?
No questions, David.
You have a question?
No, I said no questions.
Okay, so now remember what I wanted to say. So you see how we normally wrote it? We wrote it as this one's supposed to be 2, this is 2, 2, 2, 2, and this ends as 1.
mm-hmm.
That's how we're supposed to be normally write it, because that's how we understand the off-ball order. But Hund's rule of symmetry and everything doesn't allow that. So it has to be 1, and the other one's going to be 2. Like that. So those are the only 2 elements that have this exception on filling on all fast orders according to Hund's rule. So bonus review. What's the quantum number?
Uh,
4. And he is on 2.
Hold on.
L is on 2. Is on, let's start with
We're ending.
yeah, -2.
You want to end with -2? Okay.
With if I'm looking at that, I would say -1/2.
Correct. That's the quantum number for this element. Bonus review question. Hold on, let me pull up the thing. What is IE?
The definition or
Yes.
ionization energy?
Mhm.
Gives away electrons.
It's not giving away electrons.
Hold on, wait.
The least
It is giving away electrons, but
Remove.
excuse me.
bless you. Is the energy you need to remove that electron.
Yeah.
And EA, what is that? Not sports.
Affinity is the energy needed to absorb.
It's not energy. Electron affinity.
The amount of energy needed to absorb.
No.
No.
So one is removing. What do you do the opposite?
Receive.
Well, doesn't the other
Receive. What's
absorb?
another word for receive? What are you
Absorb?
doing? No.
Hmm.
Accepting.
It's absorbing, but what's another word for it?
Accepting.
When you add electrons. I have oxygen and sulfur. Which one will pull more electrons?
Oxygen, which one?
Sulfur.
Will be oxygen.
Oxygen will pull more electrons, yes. Hydrogen and potassium. Hydrogen and potassium. Which one would give off electron easier?
Sorry, I was on mute. Potassium?
Which one give off
You said
electrons easier?
you said potassium and what?
Hydrogen. What is it, Anderson?
Hydrogen.
Hydrogen, right. I'm just reviewing of what I did earlier. We got titanium and chlorine. Who's giving off and who's receiving?
Titanium. Titanium, where's titanium? Titanium and which one?
Chlorine
And you said which one?
is giving and which one is receiving?
Chlorine is receiving. Titanium is giving. I thought the weaker is on the left and the weaker would give off. No?
Repeat that again. You said titanium was what? Titanium was doing what?
Titanium it would be giving.
Mm-hmm.
Chlorine would be receiving.
Right. Which is stronger, chlorine or titanium?
Chlorine.
Right. Which will be harder to get rid of electrons, helium or hydrogen?
Which would be harder to give off?
Yes. Which would be harder to remove the electrons?
From helium.
Or hydrogen? Which one?
From helium?
Yes, helium. Helium will be harder to remove. And if we go up the periodic table, what does that mean?
It's more positive? Or it's stronger?
Okay,
Up.
when we go up on the periodic table, when it comes to ionization energy, what does that mean? Hope?
Yeah.
Moving up on the periodic table. Ionization energy. What does that mean? Are we moving up? What's happening?
There's an increase.
Hmm?
Isn't there an increase in energy? I don't know.
It's not, it's increasing, but it's not energy. What can you do?
I don't know.
It increases the chance to get rid of the electron.
Oh.
That's what it means. When you move up on the periodic table, it's easier to remove the electron moving up. When we're moving to the left, it's easier to remove the electrons. When you go down, it's harder to remove the electrons. When you go to the right, it's harder to remove the electrons. Which means you need more energy.
So when you go up on the periodic table, it's easier to remove electrons?
Yes, it's easier to remove electrons. You need less energy. It's low energy. Same thing with electron affinity. When you move up, it's easier to receive. When you move to the right, you receive more, you become more negative. When you move to the left, it's harder to receive. Because all it's doing is giving off. I explained it with lithium, because once you get rid of that electron, It's going to be harder to receive because it's dealing with its core shell. It's full.
Okay.
Endothermic.
Which is endothermic?
Shit. I think it's EA.
Ionization.
Is endothermic?
Ionization energy is endothermic.
Okay, and affinity
EA is exothermic because you're giving off negative energy.
Okay.
While the other one, you're receiving positive energy.
Okay. All right, I have to hop off. Thank you very much.
You're welcome.
You all have a good night and see y'all tomorrow.
See you tomorrow.
All right. Have a good night, guys.
Have a good night.
Good night.
I think I'm gonna hop off too. I'm so tired.
All right, no worries.
But have a good night, everyone.
Yeah, it's too much to process. I didn't mean to overwhelm you.
Yeah.
All right, have a good night. Rest. Any other questions?
Nope, I have no questions.
So tomorrow I'm gonna do chapter 9, touch up on that and touch up on the extra stuff. I'm gonna do the Planck's constants as well tomorrow.
Okay.
So that's gonna be tomorrow, Planck constants and the rest of chapter 9. Amani, you understand everything? Do you have any questions?
No, I'm good. I would like you go over with your sheet step by step. I don't know.
You want to go over the review sheet? Go, sure, go for it. Which one?
So let me check.
See what is this?
The first page.
Yeah, what's hard? I'm boring with drawing all the time.
What about it?
I don't even understand what the way is writing each thing. So
He's talking about the Hund's rule, which I showed you just now. The symmetry, which I showed you with copper and
okay.
chromium. We just did ionization energy just now and electron affinity.
That's on the first page. Okay.
Yes, that's the first page, right? That's what you asked me. Or am I
Yeah.
looking at the wrong page?
Yeah.
Mom, can I have more tea?
Oh, no. Oh, you mean you mean page 1, not the cover page. I'm looking at the cover page. Okay. So you mean the EMR, electromagnetic radiation?
Yes.
Okay, I can cover that.
You did, but we did it in the classroom. As I said, a lot of people weren't there for that. So we did in the classroom, remember, at school.
Yeah, I did that one. I covered that one in class. You couldn't make it.
Yeah.
And I couldn't record it. All right, so for this one, I hate it, but I'm gonna cover what I know so far because I have to add the the rest of the
The-
stuff that he's
The
asking for,
centimeter, yeah.
the centimeter and everything else. So I'm just gonna go what we have so far, and then I'll explain the rest tomorrow. Okay.
Okay.
Alrighty then. Let me go back to my notes.
I'm gonna hop off, okay, guys?
All right.
If anything, I'll talk to you tomorrow, okay? Have a good night.
Good night. I'll see you tomorrow.
Good night. Thank you, David, again.
You're welcome. Rest up.
Yes, you too, brother.
I have to finish this thing, so I'll try my best. All right, so this is what we're going to cover on right now. Electromagnetic radiation. So it's all about waves. So I'm going to draw the wave.
Yo, I'm taking my class now. Sorry, David.
It's okay. Just know I'm recording.
Sit down. I'm gonna give you the tea.
All right, so I'm going to explain to you each part bit at a time, okay?
Okay.
This part here, this one is called the wavelength.
Mm-hmm.
This is the wavelength where I put the arrows.
Oh.
From peak to peak, this top part here is called peak. Okay.
Okay.
This part here, it's called trough. I'll write it down. So wavelength goes from peak to peak or from trough to trough.
Okay.
Wavelength, the symbol for wavelength is lambda, the Greek symbol lambda, which is this.
Mm-hmm.
So that's wavelength. Okay.
Yeah.
Now the next one is a little bit tricky, but I think you can get it. Can you erase that? We're going to be doing frequency.
Okay.
Which is this. It's like a V.
Mm-hmm.
This is delta. This is not delta. This is a Greek symbol nu.
Okay.
How it looks here, I will show you. Make it smaller. Goes from, yeah. This is a frequency from point here all the way to point here. Well, on the line. Here. That's one cycle, also known as one frequency.
Mm-hmm.
So you need this here, we need this hump and this hump down and bottom to equal one frequency cycle.
You mean the bottom part?
Yeah. This here and this here is called an amplitude. Or amps, as people call it.
Okay.
Funny thing, this is all chapter 7.
Okay.
Frequency is also measured, and this is also written as hertz. HZ. He's not going to give us problems with it. That's the thing. He just wants you to understand how it works.
So you mean you think it's gonna give us like an image like that?
You saw I asked him the question, are you going to give us problems, math problems? He's like, no, it's not really math problem that you need. You just know the thing.
Okay.
So this is right now we're just dealing with waves. Okay, this is just waves, the explanation of a wave. So frequency is one of these and one of these, one up and one down, 2 amps, one going up and one going down.
That's the frequency.
That's the frequency.
Okay. So you mean there's it's only 2 frequencies?
Huh?
It's 2 frequencies or a 3?
Right, what I drew here, you can call 2 frequency. Yes, there's 2 frequencies here.
Okay. So what about the right part?
The what?
The right part. That's
You
the
mean
left part. There's 2 frequencies on the left part. So on the right, I think there's no frequency on this.
Okay, okay, I think I confused you. Okay, right here, I'm going to circle it. This here is one frequency. This here is another frequency.
Oh, okay, got it.
So the definition for frequency, I'm going to write it here. Actually, I'm going to write everything here. I'm going to erase the board. I'm going to write the thing.
Okay.
There you go. Wavelength is the distance between identical points on successive waves. I showed you from peak to peak or to trough to trough, the humps. That's a wavelength. The frequency is the number of waves that pass through a particular point in 1 second, what I just showed you. That one up and one down, and as many of those times passes through one particular second, that considered as a frequency. These are the symbols, symbol nu and symbol lambda for wavelength.
Okay.
Now the next part we're gonna touch on is that was just a regular wave. In the book, a regular wave is called U.
Okay.
U, or the Greek letter U with the line, sorry. Like that, a long U. That's for a regular wave, just a regular wave. Now, being more specific, what he taught us is he's talking about the wave of speed of light. Light travels in waves.
Okay.
So the symbol for waves, mean for the speed of light, is just C. And as I was telling Henderson and them that the value of speed of light is this. Hold on, I'm gonna erase this.
You mean the velocity of light?
No, velocity is the frequency. Oh, yeah, velocity, yeah, speed of, well, we call it speed of light. Same thing, velocity, speed of light, yeah.
Okay.
velocity of light or speed of light. But yeah, this is what it is. It's 10 to the 8th power. So it's not 108, it's just 10 to the 8th power. Meters per second.
Oh, it's like 3 times 108.
3 times 10 to the 8th power.
Oh, okay, got it.
This is a rounded value. 3 times 10. The actual is 2.999. It extends 2.999999999. That's the actual value. But we round it up to 3.
Got it.
I don't know why is it doing that.
So I see on the back on the review sheet, you put like 10 to the 10.
Yeah, I'm gonna explain that right now. That number that I gave you, the 10 to the 8th power meters per second, only works with nanometers. That is for nanometers, the one I give you right now. The one he gives us, it's centimeters per second.
Oh, okay.
That's meters. This is 10 to the 8th meters per second. You convert it to meters because the formula for speed of light is this. C equals, where did I put it? Yeah, lambda times frequency.
Yeah.
So these two equal this value. Because the frequency, for this to work, you need to turn frequency into meters. It's like how we did the molarity, remember? So it's the same thing, it's just now you're using waves. Now it's all about waves. New numbers to remember, plug it in the formula, all that. He's not gonna give us questions because I don't see it. I don't see it in the review sheet. He wants to give us questions. Just as long as you know the formula and how it works, how to get centimeters and how to get seconds.
Velocity of light equal to frequency and wavelength.
Wavelength times frequency.
Yeah. Okay. Like I'm confused, and the review sheet, like it put V equal frequency time wavelength. That's confused me.
Where do you see that?
And the review sheet.
He wrote V equals frequency times wavelength.
Yes.
Yeah.
V is not a frequency.
You're mixing up, you're confusing the letters. We just told you. C is another word for velocity. Speed of light.
Oh, okay. So I can put C or V, right?
Yeah, look, he wrote on the bottom, C.
Okay, got it.
He wrote the word V, so you can understand it's velocity equals frequency times wavelength. And he wrote it with the symbols. C equals lambda times nu.
Okay, got it.
Yeah. So if I'm understanding here, I guess to get wavelength, you do centimeters divided by cycles, and the other one is cycle divided by seconds, I guess. But I really have to look back at the textbook to understand this part. But that's just the basic intro of what the wave is.
All right.
This corresponds to the Bohr's atomic theory on this part of quantized orbitals, quantized energy, and quantized, what is it? Radius or radii, something like that.
Yeah.
And electrons give off light when they move from outer to inner orbital. That
So
part you
we
need to
just
remember.
that, right?
Huh?
We just did that. The for hydrogen atom, atom.
I did the second part. I did the second part of the theory, which is the quantum numbers.
Oh, okay.
I didn't cover this part yet, which is why I wrote on my WhatsApp. I have to update my thing. So yeah, that's pretty much all you need to know about frequency and all this stuff. That's it. Just know that this one here is meters per second, while he's giving us centimeters per second.
Okay.
And how I wrote it here is this. How to convert nanometers to meters, you need this. I don't know why you're doing that. One nanometers equals 1 times 10 to the negative 9 power meters.
Repeat that again.
1 nanometer equals 1 times 10 to the negative 9 power meters.
Okay. So you think it's gonna like ask me?
So if you know that, then 1 centimeter would equal 1 times 10 to the negative 10 meters. That's how he wrote it.
Okay. Got it. So if we're gonna look for frequency, it's like velocity over wavelength.
So if you want to get frequency, you do velocity over wavelength, yes.
Okay.
And if you want to get wavelength, you do what?
Velocity over frequency.
Velocity over frequency, yeah.
Okay. Oh, and the unit for frequency, it's cycle by second.
Is it what now?
The unit for frequency, it's cycle by second.
It's a cycle by second, yes. And I just realized it's not negative 10, it's just 10. For centimeters,
Okay.
it's just 10. 10 to the 10.
So it's one time 10 to the 10.
Mm-hmm.
1 time 10 to the minus 9. Negative 9.
Yeah, that's for nanometer, yeah.
Okay.
Because if you do the math, it makes sense. Because 100 centimeters equals 1 meter.
So do you think it's going to ask for the formula, not math part?
He might just ask you just the formula, yeah, the formula. And if you get this, what do you do to get this? And what do you do to get that?
Okay.
But like I said, his review sheet is not helpful.
Okay. So how about with the part below the EMR? So I can even understand the way he's writing his thing. Yeah,
What part?
below the EMR.
Yeah, I just told you about that. I just told you I only did part 2 of the theory. This is part 1 that I have to really have to read the book for this part.
The peripheral what?
Quantized orbitals, quantized energy, quantized radius, I think.
Yeah.
This basically pretty much you're using the EMR to get these orbitals to function with light and everything, how it's basically how they found the electron light.
Okay. Got it.
Yeah, and everything else I covered here is pretty much what I just did today with the p orbitals, s orbitals, electronic configuration, the principles, Hund's rule, the spins. And he goes right here. He says typical questions. He will like for this one. He says list and explain 4 components of the Bohr atomic theory.
So, which page? What page?
That's page 5.
Okay, let me get. Okay. List and explain 4 component of. Okay.
You see, list and explain 4. So it will be that page that you see there on page 1.
Okay.
That's 4. That's one of the lists right there, and then we just explain it.
We feel the math part. That's like.
There's no math involved. Just it's all descriptive. He said, remember, all descriptive.
Yeah.
And then the next part says, name the 4 quantum numbers, the symbols. You know, L, N, L, ML, MS.
Yeah.
And then it said, explain the physical meaning of each quantum number. So N, you just put the definition. What is the definition of N? It's the principal quantum number definition. L, it's the angular quantum number definition. ML is the magnetic quantum number definition. MS is the spin, is the electronic spin definition. That. And then next one is explain the physical meaning. Well, I just did that. And then the next one is give me the values of each quantum number. So if they give you a value, so what's the values of N? 1, 2, 3, 4. What's the value of L? L0, L1, L2, L3, and L4, depending on which shell you're on. So we're going to put them all together, make a chart. N1 would have L0.
Yep.
ML will be 0. And the spin would be both positive and negative.
Yeah.
Like that.
Okay.
And then the next question is, what is the off by filling order? So you should know the order. The order is going to be 1s, then is 2s, 2p, then is 3s, 3p, then is 4s, 3d, 4p, and like that.
Oh, you mean 1s, 2s, 2p?
Yeah, without the little number on top, just the order.
Oh, it's like S, 1s.
Mm-hmm.
And
2s.
2s.
2p.
2p. 3s. 3p.
Yep.
For 3D, like that?
No, there's no 3D next. That's not the order. Remember the periodic table.
Oh, for S and for P.
You're skipping. You missed the middle part.
Then the middle part is not 3D.
Yeah, it's 3D.
I said 3D.
Oh, I didn't hear you. Sorry. So yeah, it's 4. So it's 4S, 3D, and then 4P.
Okay, and it's 5S.
Mm-hmm.
4P, right?
4D.
Okay, 5P, and so
5P, and so on. The 6 becomes a little bit more complicated. It's using the F.
Yeah.
So it will be 6s.
5D.
5. No, it'll be. We just did. What was the other one? 3D. So it's gonna be 4F. I have it here. Give me a second. I wrote it down here. It's going to be, where are we? 6s, right? So it's going to be 6s, 4F, 5D, 6P.
Okay.
My review sheet helps because it gives you everything. It gives you the answers that he's looking for.
Oh, okay.
So I'm trying to finish it.
Give us the review sheet.
Huh?
When are you going to give us the review sheet?
When I'm done. When I'm done, I just finished chapter 8 today, and I'm just starting chapter 9. And then when I saw that he's doing a review, there was chapter 7. I'm like, great. So I'm just gonna give you guys right now. Well, when I finish it, I'll probably finish it tomorrow.
Okay. So what
No,
time is the session tomorrow?
Tomorrow, I'm gonna let everyone know what time. It's probably gonna be in the afternoon, same time around 5. Because I have something to do in the morning.
Okay, great.
And for the review sheet on the professor, he even wrote a question there. It says, give me the electronic configurations. Practice with those.
Okay.
Practice with those, write the quantum number, write the spin, so you can get an idea on how it looks. And the last part here is just the electronic the dot structures that I went over yesterday.
Okay, I got it.
With the plus and a negative charge. He just wants you to find the charges. He's specific on this one. He's specific on this one. He wrote a star. So he wrote, give me the charges of the indicated star atoms. So he wants you to give you the charge on the end, I guess.
So when he said, give me electronic configuration for, and in page 5.
Mm-hmm.
Okay. I feel like it's the same question on page 4. On page 4, electronic configuration for helium, hydrogen is the same question, right?
Question 4. What do you mean?
No, on page 4. Page 4. Is the same question.
Page 4, there's no questions. Page 4 is just talking to you about electronic configurations.
Why? It's the same thing. Like, he gave us like electronic configuration, and on page 5, he asked for electronic configuration, right?
Yes.
Okay.
He's okay, let's do this one. Let's do number 5 right now.
Okay.
Give the electronic configuration for part A. Silicon.
Oh, it's like 1s2, 2s2. Can I start with neon?
Yeah, you can. That's actually much easier to write it like that.
Okay, neon and.
Hold on, let me write it. Let me help you write it. So neon for the core. Then what you write?
3s2.
What?
Like neon is like 2p6, right?
Mm-hmm. What's the next we're starting with?
3s2.
3s2, okay.
Are you strong enough? Do you look strong?
Next.
Like wait, it's like 8, 14, 12. It's 3p1 and 3p1. Not good?
Yeah,
Okay.
that's it. And that's how you write it. That's what he's looking for. He wants you to split up the P's. You're technically the correct answer. You're supposed to be this 3P2. That is the correct answer, but he doesn't want you to write it that way. He wants you to break it up. He wants you to see that that the P's needs to be filled up first.
Oh, okay. Got it.
So that's basically how you answer that question right there. That's what he's asking for. Then you got the next one, which is, I think, calcium. Yeah, that's calcium. And then you got the other one, which is, I forgot what that is.
Okay.
That's not silver, is it?
What you said?
That's not silver, right?
Yeah, it's silver.
That's silver?
SI?
Oh, Si is silver. So Se is silicon then. SC.
I think so.
Well, one or the other. But yeah, that's pretty. Oh no, silver is S. Right? I forgot. I forgot. Because I know gold is Ag.
With our periodic table.
Huh?
Hopefully gonna let us look at the periodic table because that is confusing me. Yes. So
and for the last page,
yeah.
The last page, number 7 and 6, he wrote the element, he wrote the structure.
Yes.
It's so weird that H2O is missing the 2 lines, but I don't know. That's what he wrote it.
H2O.
Yeah.
Yeah, maybe he forgot to put the electron then.
Same thing with the other ones. SO3. Then you got PCl. That's a Cl, by the way. He just wrote it weird. That's potassium and chlorine. No, not potassium. That's plutonium and chlorine.
SO3.
Number 4.
No, number 3.
Number 3 is SO3.
Okay.
And number 4 is PCl.
Cl5.
PCl5, yes.
Yeah.
And the next one is sulfur.
So what's going on with the other electron for Cl? It didn't put them. Like, that's crazy.
Yeah, he didn't put the other lines as well, right? But the thing is, like, I wish he explains. Like, it doesn't explain which element can consume more stuff. That's what just pisses me off. It doesn't explain. So that's why I want to break down more in chapter 9 tomorrow.
Okay. So I have another question.
Mm-hmm.
What is it again? The Pauli exclusion principle?
Pauli exclusion principle, which means it has to do with quantized number. All the numbers cannot be the same except the spin. I mean, the numbers, all numbers. I'm gonna have it here. Hold on. Let me get my definition. Oh shoot, that's what happened. Okay. No 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. That's what it has to do with Pauli exclusion principle, the quantum numbers. So remember in the p orbitals, the s orbitals, the d orbitals, I'll give you a chart on the quantum numbers. Mm-hmm. On the p, there's 6 of them, 3 positive and 3 negative because of the principle.
Okay.
Same thing with the d orbitals. That has 10, 5 positive and 5 negative. S orbital has 2 positive and negative.
Okay.
questions?
No, I got it. Thank you.
Yeah, so tomorrow I'm gonna cover again electronic the electromagnetic radiation, chapter 9. Because this one is talking about Planck's constant. It's stupid.
Got it. All right.
All right, so did you understand everything that I explained, or?
Yeah, I understand.
All right, so then pop question then.
Mm-hmm.
Pop quiz question. What is electron affinity?
That when the energy we need to accept electron, right?
There's no energy involved.
Ah,
It's exothermic.
yeah, I forgot that.
It means you're adding an electron and it becomes negative. It gives off negative energy.
Yeah. So that means accept electron, right?
Accept electron, yes.
Okay. Got it.
And ionization energy?
Remove electron.
Remove electron, the energy you need to remove it.
Okay.
It's measured in kilojoules. But again, he's not going to access how much energy you need to remove this electron. He just wants to know the concept.
Okay.
Okay. And
okay.
which side will give you more, which side would receive electrons on the periodic table?
The right side.
The right side. And the left side does what?
Give up. Remove.
Give away. Yeah. No, gives up electrons. Yeah.
Yeah, give up electron.
And when we go up, what does that mean? When it comes to electron affinity, when we go up, what does that mean?
It's easier to remove electron.
It's easier to accept.
To give. Oh, when you say go up on the left side?
Electron affinity.
Oh, okay. Yeah. Easier to accept electron, you said?
Mm-hmm. Mm-hmm.
Okay. Got it.
And when it comes to ionization energy, when you go to the right?
To the right.
Ionization energy, i.e., when you go to the right, what does that mean?
Oh, it's like to accept.
You need more energy to remove it.
Man, that's like, that's the opposite, right?
Exactly.
Okay.
You getting it? It's the opposite, right? You're getting it.
Okay.
They're both the same direction, but just one is doing the opposite of the other.
Okay, got it.
So one requires more energy more energy to receive, easier to receive, how I say it. And the other one is you need more energy to take out the electron.
Oh.
It's harder to take out. Easier to receive, harder to take out.
Okay.
That's how I simplify it.
So the easier to receive, it's EA, right?
No, that's just what it is. EA means you're accepting electron.
Yeah.
Easier to receive will be the element. He, Ne, argon, Kr, Xe, Rn on the periodic table. Those are easier to receive.
Okay. Got it.
But it's also harder you need more energy, so it's harder to remove.
Mm-hmm.
That's the ionization energy. You need more energy to remove that.
Okay.
You understand? You understand why, right?
Yeah, because they have more electrons, right?
No. No. All right, I'm gonna draw. I'm gonna do a quick one. I have to draw it so you can see it.
Mommy.
Oh, wait, I'm busy. Going to pee? Go.
Come.
I will cover you. Go, baby. Go. You're a big boy. No, I'm not going to touch your thing.
I'm gonna use two elements, okay? Simple elements.
Okay.
Just use this one.
Yeah. It's not working.
So these two elements are here.
Mm-hmm.
This one is hydrogen. This one is
Na?
Na.
Okay.
Which electron will be easier to remove?
Hydrogen.
Hmm?
Hydrogen.
Hydrogen will be easier to remove.
Yes.
Wrong. It's tougher to remove because it's closer to the center. This is easier to remove because it's farther away from the center.
Oh, duh.
That's what that means.
Okay.
So that's what ionization energy means. You need more energy here to get rid of this electron than you do over here.
Got it.
But who receives electron easier?
Receive electron easier. Hydrogen. No.
To absorb electrons easier?
Yes.
Na.
That's confusing me. I remember you did an example with an ACL.
Mm-hmm.
I understand that one. So this one now. So hydrogen is harder to remove electron, right?
Mm-hmm.
Because it's close to the center.
Mm-hmm.
Okay.
This is more negative.
Okay.
It's more negative, but the difference between this has a +1 and this one has a plus what?
+9.
No.
+1 too. Because it's
11.
11.
Yeah.
Oh.
Now you see why it pulls more?
Yes. That means an A is
Can be more negative.
Is easier to give electron, right?
It's easier to give off electrons, just like hydrogen.
Okay.
But technically, I know this is a bad example. Technically, they don't absorb at all, but I'm just using it so you can understand the concept. Na does not absorb anything at all. It just gives off.
Yeah, that's okay. But if you can we do the NaCl again?
Okay. So you go, as remember, as you go to the right, you get more negative. Okay.
Yeah.
All right. So let me do this again. Let me do Na again. Na. Cl. This extra stuff, the connections and everything, is pretty much what you learn in Chem 2.
Okay.
This is just the intro to this. Chem 2 explains more about these connections and bonds.
Got it.
2, 3, 4, 5, 6, 7, 8, 9, 8, 8, 9, 11. This one has 17. So wait, let me do that. 2, 3, 4, 5, 6, 7, 8, and just 7. Six, 7. Okay. Right now they're neutral.
Mm-hmm.
These two connect. You
Yeah.
bring them together. So the process is doing this now. This is coming off, going to here because it's receiving.
Yeah.
This has a plus charge of 11. This is a plus charge of 17.
Yeah.
So it receives and now it has this. Now this is happy.
Okay.
Its shell is full. That's what it wants. That's what Cl wants. Cl wants to fill its shell. So it just needs one electron to fill its shell. And now since we added the electron, it became, this process was called the EA.
Yeah, the other one is
Became a
IE.
negative, and this one was the IE.
Okay. So my question right now,
Positive.
we the like is Na is easiest to give electron, right?
Yeah.
Okay.
Na is easier to give up because you see it's farther away from this. This electron is so far away, it can just say bye-bye. But this is the proton is so strong on this one, is that it wants more. It needs one more to be complete. It's not happy. So it steals this. Give me, it's mine. Now it's over here. It's happy. But now since you add more electrons, it became negative. And since you take it off, the math, as we did here, now we have 10 electrons, -1. Now we have more electrons here. It becomes 18, -1. I mean positive 1 over here.
Yeah.
And because this is positive and this is negative, these two can connect together to become an ionic bond to be neutral. Together become NaCl neutral.
Mm-hmm.
And that's how we get salt.
Got it.
Sodium and chloride, salt. Why? Because of the ionic bond. I use water because water is also an ionic bond, but it's really more, it's different, it's difficult. Water is a mixture of covalent and ionic. They call it polarized.
Mm-hmm.
They call that one polarized because the electrons dance with each other.
Okay.
But this one here, they don't dance. They just take it away. It's mine. Boom, let's connect. So as this one goes away, it loses its shell. And it's like that.
Okay.
But the crazy thing about it, how this works with water, water separates these two together to bring it back to what it is. NaCl, and the water, hydrogen and oxygen, replaces the missing stuff.
So you mean H2O, it didn't give up the electron, they just share?
H2O, yeah, they just share.
Okay.
They share electrons, H2O. Because of that sharing, let me write it here, H2O. H, the O, and the H. This has 1, this one has 1, and this one has 6. They're connecting here, they're sharing, and this here is sharing. But when you put it in water, the hydrogen is going to connect to here, and this is going to connect to here, to the oxygen.
Okay.
When you put it in water, that's how it's happening in the water, chemically wise, with the electrons and everything in the tiny or molecular level, microscopic level.
Oh, and hydrogen, which part is EA then? The oxygen is EA?
But they're both. It's doing both.
Oh, okay.
It's doing both because it's polarized. They're sharing, so it's doing both. It's giving out both EA and IE.
Okay.
Do you want me to draw it out again?
Yes, please.
With the water?
H2O.
Okay, so let me end the thing because it's I already covered this. Let me stop not the share. Stop the recording. My computer is freezing. Hold on, just let me stop the recording really a second.